On Tuesday's class, we talked about standard deviation, and today we're going to go over normal distribution, which is in the statistics world where we normally see the most standard deviation being used. So when we look at how data can be distributed, and we have a couple histograms here, we can see that it can be spread in different ways. So if you look at this first example, we look at where most of the data seems to be condensed. It looks like the data is more to the right. Right, you can see this right here. That's where the bulk of the data is. Whereas in the middle graph, it looks like the data is more to the left. And then in the last example, there's not really a clear area where the data is mostly condensed. You have this part over here that looks like a big collection of the data, but then also in this area to the right you have quite a lot. So in this case we just say that the data is randomly distributed. Okay, so when we talk about normal distribution, what we talk about is how some data sets will form a curve in the shape of a bell when they're graphed. And we call this a bell curve. And so a bell like this that hang in the churches, right? And so it looks sort of like that, and so we call it a bell curve. And when data is distributed in a bell curve, then we say it's normally distributed. So when we talk about normal distribution, what we mean is if it looks like a bell curve, it's normally distributed. And most measurements of living things, so all the information that we gather about ourselves, so mass, height, lifespan, all these kinds of things have normal distribution, okay? And including things like IQ and all sorts of things. So when we look at this bell curve here, what you can do is draw a line down the center, and then on this side, so on either side, so if we go here, so here's my line down the middle, this side, oh, you guys understand my pain here. Okay, so on either side of this line, there's 50% of the data. Okay, so if we split our bell curve down the middle and look at either half of that bell curve, you should find 50% of the data. And of course, when we look at that middle, that's going to be what we call our mean. So when we put that vertical line of symmetry or that dotted line down the middle, we call that the mean. And we have a new symbol for mean, and it's called mu. So it's like a U with a weird little tail on the beginning. So that center line is the mean. And then in a normally distributed bell curve, the mean, median, and mode are all very close values to each other. They all fall under the curve, and then when they all fall under the curve, it means there are no outliers. All of the data, 100% of the data, will fall underneath the curve. And this is where we can bring in our standard deviations. So when we start with our mean, which is of course the line down the middle, like that, what we can do is move in standard deviations away from the mean. And so we were working a little bit with this on Tuesday when we talked about Elsie's hours. So Elsie worked 21.5 hours on average. And she could, or was it 21? Oh, we'll say 21.5. And, I think it was 21. Okay. And she could work 1.5 hours on either side. So 1.5 was the standard deviation, the sigma. So she could work this way sigma, 1.5, or this way, 1.5. Okay. And it's the same thing here. So when you start at your mean, you can move either direction. And so you'll see how it's broken down here. You have mean plus 1 standard deviation, mean plus 2 standard deviations, mean plus 3 standard deviations. And then just like on the number line, when you go to the left, you subtract. So mean minus 1 standard deviation, mean minus 2 standard deviations, and mean minus 3 standard deviations. And the reason why the bell curve is so popular in statistics and in information gathering is that it breaks down really nicely and consistently. So between 1 standard deviation on either side of the mean, 68% of the data is contained. So you have 34% on this side and 34% on that side. And then within 2 standard deviations on either side is 95% of the data. So if we were looking at people's height, 95% of people, say men in a country in Canada, would fall within 2 standard deviations of the mean. So very few people stand on the very far ends of this bell curve. So to add that, we'd have 13.5% over here and 13.5% over here. Okay, and that would be 13.5 plus 34 plus 34 plus 13.5 would equal 95. And then on the so here, within 3 standard deviations, you have 2.35% on either side. And so then within 3 standard deviations of the mean, you have 99.7% of people. And then over here, it's difficult to see, but over here would be within 4 standard deviations. And if we drew our graph like this, there would still be a tiny bit of space over here. And so over here is 0.15% of the population. And when data distributes itself normally or along the bell curve, it really helps us see trends in data. So what percent of the data values are below or equal to the mean? So we look at the mean, which is our center line here. And we want below or equal. So it's everything to the left. And so everything to the left, if we're assuming 100% of the data is contained under the curve, we'll have 50% of the data. And again, here's our bell curve, there's our mean, so it's 50%. What percent of the data values are above or equal to the mean? So if I draw my bell curve again, and there's my mean. If I want to go above or equal to the mean, I go to the right and I fill in this half, and again, it's 50%. And then what percent of the data are within 1 standard deviation of the mean? And when I go back up here, here's my mean again in the center, and here's 1 standard deviation up or down and 1 standard deviation up. So it's this part here. Okay, so if I go back down and draw another little bell curve. So here's my mean, and there's 1 standard deviation. So that's adding 1 and subtracting 1. And so I get 68% of the data is within 1 sigma, or 1 standard deviation. Okay, so let's look at a fairly common example. So IQ scores, whether or not these are valuable at all, but when we talk about IQ scores, they are almost always normally distributed. So the example below shows the IQ scores for a population of people that had a normal distribution. So of course we have to depend on what population we're doing. So if we were doing a distribution of IQ scores of PhD students at MIT, which is a very prestigious high-tech school, probably they'd be a little bit above normal, but this is just a normal population. And so if we look here, let's answer the questions. So what is the mean IQ? So I look at my bell curve and I identify my mean, which is this center line here. So in that case, my mean, and remember that we show mean with this little symbol there, my mean is 100. So if I want to write that out, I would say the mean IQ is 100. Okay, what is the standard deviation of sigma or sigma? So I have to look, and it naturally breaks it down, so I have these natural color barriers to show me where my standard deviations fall. So I have to see how much from the mean they differ. So if I go from the mean to the first standard deviation, my mean is 100, my first standard deviation is 115. So that's a difference of 15. And then let's go the other way to make sure. So between 100 and then if I go down one standard deviation here, it goes to 85. So 100 minus 85 is also 15. So, and we can test it again to go this way if you want. From 115 to 130 is also 15. And from 85 to 70 is also 15. So that tells me that my standard deviation is 15. Okay, and so what we can do is, and we can test that. So if we go mu plus 15 should equal, and again, if we go back and look, so when I go one standard deviation, mu plus one standard deviation should be 115. And I know that mu is 100, so I go 100 plus 15, and that's 115. So that's checked. So my standard deviation is correct. How many people have an IQ between 70 and 130? So if I go up here and I look, so here's 70, and so I want to know how many people fall within this distribution. And if you flip back, so that's within 2 standard deviations of the mean. So how many people will fall within 2 standard deviations of the mean in a bell curve? And if you flip back to your first page, you look here within 2 standard deviations, and it is 95%. So this line here. So this is mu plus or minus 2 standard deviations, and that will be 95%. Okay, and we can then label on here, I'll erase that out. So if this is mu plus sigma, mu plus 2 sigma, and mu plus 3 sigma. And over here it's mu minus sigma, mu minus 2 sigma, and mu minus 3 sigma. Okay, so then the next question is, a person has an IQ of 145. Is this common? So go find 145, which is over here. Okay, and when a person has 145 IQ or higher, they fall in this tiny little area over here. So if we look at this area over here and the whole rest of the graph, is an IQ of 145 common? And the answer to that would be no. So an IQ with 145 falls well within what we call the genius range. And so these are people who are incredibly smart, people like Isaac Newton or Albert Einstein, possibly even someone like Steve Jobs. How many standard deviations of the mean is an IQ of 145? So we have to look at our mean. Here's our mean as mu. And how many standard deviations over do we have to go? So we went 1, 2, 3. So this is 3 standard deviations. Okay, so let's now try constructing our own normal standard normal distribution or bell curve with the information that we're given. So 95% of people at a school are between 1.1 meters and 1.7 meters tall. Height is normally distributed. And so this tells us we're good to go drawing a bell curve and using bell curve information. Sketch a normal curve using this information. So I'm going to just start by sketching out a bell curve. And it doesn't have to look perfect, it just has to look approximately like a bell curve. And I can go ahead and draw a line down the middle, and I'll label that mu, but I don't know what mu is yet. So this 95%, again, if I scroll back and I need to find out in terms of standard deviation. So 95% is 2 standard deviations on either side of the mean. So from that information, if I look between 1.17, so again, I can draw in some standard deviations to work off of. I'll put 3 over there. So here's mu plus or minus theta, and mu minus 2 theta, mu minus 3 theta, and then mu plus theta, mu plus 2 theta, and mu plus 3 theta. And so I know that 95% are within mu minus 2 theta and mu minus 2 plus theta. And so these are my values for that. So this will be mu minus 2 theta, and this is mu plus 2 theta. So I can go down here and fill out that this is 1.1 meters, and this is 1.7 meters. And then I look at the questions. So find the mean and the standard deviation. So the mean is the halfway point between 1.1 and 1.7. So I know mean is exactly between 1.1 and 1.7 meters. So to find mean, we can go mu equals 1.1 plus 1.7 divided by 2. So that'll be 2.8 divided by 2, and that's 1.4 meters. So I can go up here and put 1.4 meters. And now I need to find standard deviation. So if I look to get between 1.4 and 1.7, there's 2 standard deviations. So there's 2 sigmas between 1.4 and 1.7. So 1.7 minus 1.4 equals 0.3 meters. So that means 2 sigmas equal 0.13 meters. Or sorry, 0.3. 0.3. So 2 equals 0.3. To get sigma by itself, I divide both sides by 2, and I end up with sigma equals 0.15 meters. So my standard deviation is 0.15, and my mean is 1.4. So if I am 1 standard deviation above the mean, how tall am I? So here, height equals mu plus 1 standard deviation. We know mu is 1.4 because we just figured that out, and we know standard deviation is 0.15, again, because we just calculated that. So this height would be 1.55 meters. And then I can go fill that in here, 1.55 meters. And you can fill in this side too if you want to go 1.4 minus 0.15 is 1.25 meters. And then the last question here is, my friend is 1.85 meters. Without looking at the curve, how far is this from the mean? How many standard deviations from the mean is this? So I'm not going to scroll up. I'm going to start with 1.85, and I want to know the difference from the mean. So we'll minus mu. So 1.85 minus 1.4 equals 0.45 meters. So how many standard deviations is this away from the mean? So it's 0.45 meters from the mean, so we answered this question. How many standard deviations from the mean is it? So the number of standard deviations will be the difference over sigma. Okay, and we were working with this a little bit last class. So 0.45 meters divided by 0.15 meters equals 3. So if we want to answer this, we'd say my friend is 3 sigma above the mean. So it would be mu plus 3 sigma. And we can test this, so we can check it. So we go 1.4, because that's mean. Actually, we can do the whole thing. Mu plus 3 sigma equals, so we have mu is 1.4 plus 3 times 0.15 equals, we don't know yet, and then we'll find out that it equals 1.85 meters. And that's how tall your friend is. So that works. Okay, I'm going to save this last example for class on Tuesday. So first thing in class, what you'll do is come in, we'll go over this example together, I'll answer any questions, and then we will write the quiz. And so the quiz is on 5.3 and 5.4. And I want you to work on the worksheet 5.4. So I'll be collecting it in class on Tuesday, but you will have some time in class. So I would get most of it or as much of it done as you can over the weekend, and then in class on Tuesday at the end of class you'll hand it in. So again, there's a quiz on section 5.3 and 5.4 on Tuesday, but first we will go over this question together. We'll go over any questions you might have, and then we'll write the quiz. So email me if you have any questions, and have a good weekend.